Okay, all right, let's get started. As I was mentioning earlier, I'm curious how you all were able to survive Friday without statics in your life. And I can see you're saying, yeah, we struggled, but we made it. That was a joke, not a very funny one. Today, I want to go through a couple of logistics, and then we're going to get into a new unit in the class, or a new module talking about the concept of a centroid. So just to be clear, attendance grades are up to date. I counted everybody present for the lecture on Friday, since we had it pre-recorded. That's a typo, because those are graded. Why did I say being graded? Whoops, let's fix that. Sorry about that. Okay, so everything through all the homework 3s, if you will, have been graded. One of the things my TAs noticed is I had a typo on my homework 3.6 solution. It was like on the very first step, I had a decimal point in the wrong place. But I was doing the math right, so the final answer didn't change. But there was the very first force I had in my solution. It was 22.53, but it was actually 225.3. But my TA noticed that, and they accounted for it when they were doing the grading and whatnot. So it didn't affect anybody's grades, but I did correct that and repost it. The split homework 4.1, 4.2 assignment is being graded. That solution is posted. Homework 4.3 is due today. That solution should be posted on Wednesday. And speaking of, we have our review on Wednesday and we celebrate on Friday. I do have an assignment that I'm giving you today on the concept of centroids, but it's not due until the following Monday. So, you have a week on this. So that, everybody cool on logistics for what's going on for the next few days? All right. Speaking of, let's talk about the celebration. So we have our review on Wednesday. We have the exam on Friday. Same rules as before in terms of formula sheets, and same concepts that we're going to have in terms of, we'll have a review on Wednesday where you all can ask whatever you want. The exam will be of the same format as it was the last time, a series of conceptual questions and then a few computational problems. I will tell you, I have done my best to minimize the amount of 3D on the exam. There is a little bit on the exam, I'll tell you, but it's not the majority, okay? So, because I know it's a timed exam, and I know 3D problems can get to be kind of long. So, I've done my best to try and minimize that as much as possible. So, everybody okay with that? So, what I'll say is on Wednesday, come prepared to ask questions about what's going on the exam. And I'll go ahead and tell you, today's topic on centroids is not on the exam. And I know that it might be, there might be a temptation to sort of roll your eyes and let this stuff sort of wash over you, but you do have a homework assignment on this due next Monday, so I definitely want to make sure that you're paying attention to this. Okay, everybody get the code? All right, let's go ahead and dive into the land of centroids, okay? Now, just to set the stage, there is an old saying that this class is only about two concepts, forces and moments. And so you could argue that we're sort of done with that. We've talked about forces and moments and, and hammered them into the ground. So what's next? Well, I would argue that what we need to do now is see if we can take those concepts and apply them to some fundamental engineering problems that show up in a variety of different disciplines and a variety of different arenas. And so one of those challenges or one of those concepts is to try and determine the center of gravity of a given body, okay? And that's a valuable skill. I don't care what discipline you're in. That's something that you need to be able to do. But I do want to give you a little bit of motivation. So let's consider these shapes. Okay, so I have a circle and I have a square, okay? And I would argue that for these shapes, it's pretty easy to determine where the quote-unquote center is, right? If we're talking about a circle, the center is probably about right there. If a square, it's about right there. I think that's a pretty straightforward question to ask. But maybe a more realistic one is, what about this? Where's the center of that? Or maybe even better, how would you even define what the center even is? So can you come up with a systematic way of defining what the center is and locate it for any shape, okay? Now, you might go, okay, Dr. Mike, you defined a very, funny little geometry problem, but I'm an engineer. I'm not a mathematician. So who cares? Why do I need to know this? Okay. Well, let me give you a couple of examples. Now, by the way, just to throw in the term here, we have a name for the center of this shape, and the terminology that we use is what's called a centroid, and we're going to define that rigorously here in a bit. But why do we care, and where does this affect engineering? Well, the short answer is that engineers don't always deal with shapes that are quote-unquote easy, okay? We have a lot of cases where the cross-sections that we deal with, the rigid bodies that we deal with, are not pretty rectangles and circles and whatnot. They're complex geometries that are designed to withstand the demands that they're subjected to. For example, if you look at the cross-section of a dam, that's not a simple square or a circle. That's a weird shape, okay? For you mechanical engineers, what about this? What about the cross-section of a wing? Okay, where is the centroid of that shape? That's not easy to just determine, okay? And for you biomedical engineers in the room, determining the center of gravity or the centroid of a bone cross-section or the cross-section, the centroid of a medical device, I could go on and on, okay? But we don't get to avoid this. So the point is, we don't get to just deal with simple shapes. We have complex stuff that we have to deal with, and we need to be able to address them, okay? So what I'm getting at is understanding and learning how to locate the centroid is very critical to understanding how we deal with distributed forces and moments on a rigid body. But as I say here in this little blue note here, maybe I'm getting a little bit ahead of myself because I haven't even really defined what a centroid even is, okay? So let me try and rigorously give you an example of what a centroid even is, okay? So let's start off simple, okay? Let's consider a flat plate. So I'm using a plate, and the reason I'm using a plate is because we're considering something of uniform thickness, okay? And so what we're going to do is we're going to cut the plate up into a bunch of tiny elements, okay? So this image doesn't do the best justice of it. So let's say that, here's your plate, okay? And so what we're doing is we're taking it and we're sort of cutting it up into a grid of elements. And so I'm not going to draw all of them, but imagine you cut this thing up into a grid of elements. And let's say we consider, that element right there. I'm just picking a random one, okay? So if we look at this element, we'll call it element 1, okay? Now this element, I've defined this as sort of a square, one of those simple, easy to understand shapes. So I can determine a center or a location for that square right here. We can call that, we'll say x1 comma y1. So for example, if I have a coordinate system, right here, so that's the x-axis and that's the y-axis, okay? I can determine, the coordinates of that right there, we'll call it x1 comma y1, and we'll say that that element has some weight, okay? So I'm going to call it delta w sub 1. Delta just meaning it's just an increment of the plate, and we'll say sub 1 because it's element 1, okay? So for each one of these elements, I can define where it is, and I can define the weight, okay? Now I can do that for all of the elements in the plate. I can say, okay, here's an element, here's an element, here's an element. There's oodles and oodles of different elements on the plate, and each element has a weight, and then it has a coordinate as to where it's located, okay? And I could say, well, I just got done with these, last couple modules in Engineering 213, and I understand I can apply the equations of statics to this. I can look at sum of forces and sum of moments. Let's see what we've got. So if I sum forces, okay, so based on my coordinate system, my plate is acting in the direction of gravity, right? So it has a weight and forces that are being applied along the z-axis. So I can sum forces along the z-axis, and basically what I'm getting is the sum, the sum of all of these different weight components. With me so far? Now for the moments, okay, so check this out with the moments. So let's sum moments about the x-axis. Okay, so if I sum moments about the x-axis, what I'm saying is a force times a moment arm, okay? The force is the weight of these elements, but the moment arm, think about it like this. How far are you from the x-axis? So if I use this element, this image here up top, if I'm looking at this schematic right here, how far am I from the x-axis in this case? Well, it's y1, right? So for where I'm summing moments about the x-axis, I'm saying the force times the moment arm and it's y. Force times the moment arm and it's y, and so on and so forth. Likewise, when I sum moments about the y-axis, it's these forces times the x distances, right? So there's the point I'm making right here is there's an exchange of the subscripts, right? So if I'm summing moments about the x-axis, I'm multiplying by y distances. If I'm summing moments about the y-axis, I'm multiplying by these x distances. There's a flipping of the subscripts, and that's not a mistake. Okay, that's on purpose. Does that make sense? You're going to see that pop up again here in a bit. And I just wanted to make sure that you saw that, hey, that's not Dr. Mike making a mistake. That's actually correct. Okay, with me so far? Now, so if I want, okay, what I can do is I can locate what I'll call the center of gravity, and there is a difference between the center of gravity and the centroid, and that'll become clear here in a little bit. So if I wanted to define the total weight of the plate, I could just sum up all of those individual weights, right? Okay, and if I wanted to, so I can handle that. That part's pretty straightforward. Now, a question might be, okay, if I go back to this, I've got, if I'm summing forces and summing moments, I've got, what, hundreds of these little elements I got to deal with. What if I wanted to idealize the entire plate as a single vector, okay? Just a single vector, okay? In other words, instead of all these oodles and oodles and oodles of elements, I have a single vector, okay? So what do I need? I need a magnitude of that vector, I need a direction, and I ultimately need a location. Now the magnitude's easy. That's just the weight of the plate, total weight. Okay, the direction's pretty easy as well, because it's all going to act in the direction of z. Okay, what about the location? Okay, I need to find that magic place to place that vector. Okay, and where am I doing that? It's basically equivalent systems. I have to place that vector at that magic point such that it generates the same amount of moment as all of these, okay? It's an equivalent systems problem, okay? So what I'm going to do is I'm going to sum up the moments. So here's the moments about the x-axis, the moments about the y-axis, and I'm going to say that's got to equal the total weight of the plate times whatever these magic coordinates are. And by golly gosh gee, I can find these magic coordinates pretty easy. And the formula is actually really easy to remember. Because if I want to find, let's say, this magic x coordinate, I just sum up the weights times those x distances divided by the sum of the weights, okay? And likewise for y. I sum y times w over the sum of w, okay? So basically what we're computing is a weighted average, okay? Now, so what we have here are these coordinates. I'm calling them x bar and y bar. If you've ever had background in statistics, you know that if you have x bar, y bar, that sort of represents an average. Y'all ever seen that notation before? I have a feeling. So basically, this is sort of a weighted average of where to place this point. Okay, with me so far? Okay, now, up until now, this all sounds fine and dandy. The problem is that the problem with this formulation is that it depends on how big these little elements that I choose are. In other words, the bigger that those elements are, the less accurate our estimate of the location of the centroid is. So what we need to do to refine this estimate, or to really from turning it into an estimate into an actual answer, is we need to take the limit as the size of these elements approach zero, okay? But what happens in calculus when you do that? What happens when you have a region and you take the limit as the size of those slices approaches zero and you sum up those slices? you're now talking about the land of integration, right? You're talking about integrals. That's what an integral is, okay? So if we want, so from calculus, we know that if we're taking those elements and setting them and tending them towards zero, but we're still summing them up, we're taking these algebraic formulations, like right here. So we're taking this formulation, which is, sort of an algebraic summation, and we're turning it to this, to where we're integrating, okay? Because basically this just goes back to the basic definition of a Riemann sum. Y'all remember that from Math 229? I know you've seen it. It's probably been a while. Now, I have some shorthand notation right here that I've used, this x dw and this integral of dw. We'll expand on that here in a little bit. But everybody with me so far? Okay, so what we have here, though, this is my formal definition of the center of gravity. Okay, what I haven't done is define the centroid. What's the difference? Okay, well, let's get into that. Now, I want to talk about these weights. Okay, now if I have one of these elements, okay, how do I compute how heavy it is? Okay, well, a way that I can do that is I can say it is the unit weight of the material times the volume. Okay, so have you dealt with unit weights yet in either physics or chemistry or anything like that? So an example of that might be, let's take water. Okay, water weighs about 62.4 pounds per cubic foot. So if I have 3 cubic feet of water, 3 cubic feet being the volume, I can multiply it by that unit weight and get the total weight of the element. With me so far? Okay, so I can compute the unit weight, I can compute the weight of one of these elements pretty easily by taking the unit weight times the volume. But how do I compute the volume? Okay, well, the way that I compute the volume, I have like, here's one of my elements. Right? So how can I compute the weight of that, or the volume of that? Well, I propose what I can do is I can say that that is an area. So if I multiply that area by a thickness, so that being the thickness, and that being the area, that'll give me the volume. With me so far? Okay, so what I'm going to do is I'm just going to use, we'll just say, this X bar term to sort of simplify that. So if I have the weights, basically what I'm doing is I'm summing up the gamma times the thickness times the delta area, right? And then therefore, to compute X bar, what I've got is the sum of X times gamma times T times delta area divided by the sum of gamma times T times delta area. Now, the areas change from element to element, so you really can't cancel these. But the unit weight's going to be the same, and the thickness is also going to be the same. So what I can do is I can say, you know what, let's make this a lot simpler, and let's say this. So now let's remove the unit weight of the material and the thickness. So instead of computing a weighted average of the plate's weight, I'm computing a weighted average of the plate's area. Okay, so instead of dealing with weights, I'm now dealing with areas. So instead of it becoming a force and distributed force problem, it becomes a geometry problem. Okay, let me erase all my ink here because I think I've got some other stuff that's going to show up. The idea is that a lot of times when we're in the design land, we can usually think of bodies as being of uniform unit weight and thickness so that these terms cancel. A good example of that is if you're dealing with, let's say, a dam. Okay, a dam might be 500 feet long, but what we'll do is we'll only consider 1 foot at a time. and just deal with the forces on that, and whatever design we need to do, we just repeat it along the length of the dam. Same thing can be true in oodles of mechanical engineering designs, you name it, okay? So now what we have is, instead of dealing with things in terms of weights, we're dealing with things in terms of areas. This definition is going to be the location or the definition of the centroid. So if the center of gravity is expressing things in terms of weight, the centroid is expressing things in terms of area or in terms of geometry. That's basically the difference, okay? Now, before we start computing centroids for composite shapes, and that's going to be one of the key skills that I want to impart upon you in this class, we need to understand how centroid expressions work, okay? So what I mean by that is, so a very common challenge in engineering is to compute the centroid of this, okay? So this is a weird shape, okay? We've got, this polygon shape at all sorts of weird angles. But what I can do is I can take this and I can split it up into a series of simple shapes, okay? Now, it is not that difficult to locate the expression or the location of the centroid of this rectangle, or the centroid of this triangle, or the centroid of a circle, or a semicircle, or what have you. In fact, it is very common that engineers will have with them a reference that contains the location of centroids of basic shapes. Look in the appendices of your textbook. You will find the centroids of basic shapes. Look in the FE reference manual. You will find the centroids of basic shapes. What you need to do is be able to take that library of centroids and use it to compute the centroid of some composite region. And that's something we're going to do after the second exam. But for now, what we need to do is we need to learn, well, how do you compute the location of the centroid of a simple shape? And in order to do that, you got to use a little bit of calculus. So today what we're going to do is a little bit of calculus. Specifically, what we're going to do is we're going to try and compute the location of the centroid of this shaded region. Okay? So I have here the curve y equals x squared. We have that curve bounded from x equals 0 to x equals 3. And we're going to determine the location of where the centroid is for this shape. Okay? So again, I'm sorry, we are going to do a little bit of calculus this morning. I can't get away from that. I'm sorry. No real way to avoid it. But fortunately, you'll find that the calculus that we're going to do is going to be simple. I'm not trying to make your lives sufficiently challenging. You'll see that this is not too bad. Okay, so ultimately what we're going to do is we're going to determine the location of the centroid. Okay, now the way that we're going to do that is we're going to evaluate this and evaluate this. This is our eye on the prize for today. And probably what's more is we do have to take some time and define what these terms mean. Like, what is DA? What is, how are we going to do this? But I think you're going to find as we start evaluating this, this is not very, very difficult. Okay? Let's take our time with this and take it one step at a time. Okay. Everybody with me so far? All right, so the first thing that I want to do is I want to determine the area. So the area in my little shorthand is just the integral of dA, right? And that shouldn't be all that funky notation. I mean, what is the integral of dx? It's just x, right? Well, x, plus c if it's indefinite, right? But these integrals are not going to be indefinite. They're going to have limits. So don't worry about that. Okay. So let's see if we can handle this. And so let me show you how I go about it. All right, so here's our curve. Okay, so here's our curve. All right. And we have our region here. This is x equals 3. This is x equals 0. And so the first thing that I'm interested in is determining the area of this rectangle. Okay? Now that rectangle has a name. That's dA. Okay? That is a differential slice of the rectangle. Okay? We're going to determine the area of that and then sum those up or integrate. Okay? So how do I determine the area of that rectangle? Well, how do I do that? Well, how tall is that rectangle? Well, the height of that rectangle is just y, right? That's all it is. And the width of that rectangle is some differential element dx, right? So this is y dx or x squared dx, right? Because y equals x squared, right? So therefore, the area is the integral of dA or the integral of x squared dx, evaluated from x equals 0 to x equals 3. Now that should be a very fundamental problem from Math 229, right? What is the integral of x squared? There we go. So we have x to the third over 3. We evaluate that from x equals 0 to x equals 3. And so we get 3 to the third over 3 minus 0 to the third over 3, right? Bringing it back to calculus 1, right? We plug in the top number minus, plug in the bottom number. So we get 27 over 3 minus 0. So therefore, area is 9. So let me stop for a sec. Is that challenging? Hopefully that's simple. You might not have thought about it in this geometric terminology before, where you're defining this rectangle, but in the end you're just integrating. That rectangle definition is sort of valuable because of what we're going to do with the other axis when we flip the direction of our rectangle. That's a little bit later, so for now, bear with me. So far, so good? Okay. Okay. So now what I want to do is I want to integrate, I want to do my next integral, and I'm going to call it QY, but that's going to be the integral of x dA. Remember those subscripts get flipped, so that's not an accident. You don't have to call it QY if you don't want. It doesn't matter. I just need to ultimately integrate dA and integrate x dA. And the reason I'm integrating x dA is because ultimately this is what I need to determine right here. I'm trying to locate x bar, right? So I've got the integral of dA. Now I need to get the integral of x dA. So it doesn't really matter what you call it. It's just I'm calling it QY because your textbook will probably refer to it as that. But you don't have to name it that if you don't want. So this is pretty simple. So what I'm doing is I'm integrating x times x squared dx, right? Because this is dA, that's x squared dx. And I'm evaluating that from x equals 0 to x equals 3. So what do we have? We have the integral of x equals 0 to x equals 3 of x to the third dx Okay, and what is that? What is the integral of x to the third dx? There we go. Now, some of you may be wondering, this is a peculiar way of writing your limits. Probably when you took Calculus 1, your calculus professor probably never bothered to do that. They probably just said 0 and 3 instead of x equals 0 and x equals 3. Trust me, you'll see why I'm doing that here in a bit. So therefore, we have that. So if I want to find the location of the centroid, it's just this. Here, let me scroll down a little bit. Pretty simple. So we just have 81 over 4 divided by 9. I think I can do that one in my head. That's going to be 9 over 4. So x bar is 2.25. That's one of them right there. So just to make sure that we're all on the same page, if I have a plate of steel that looks like this blue region, and I want to balance that plate of steel on the head of a pin, I place that pin at a particular point. We'll call that point right about here. The coordinates of that point are 2.25 comma something. I haven't figured out what that is yet. I'm going to get to it. If you have access to a 3D printer, maybe print out a little plate like this and see if it works. So it should, barring the resolution of your print. Everybody with me so far? Okay. Now, how do I find this other point? Okay? Well, the way that I find this other point is a little wonky. So, bear with me. Let's go back to the graph. In order for this to work, what we have to do is we have to sort of think about our region a little differently. Okay? Now, what was the graph of this curve? It was y equals x squared, right? Okay? So this point here was what? X equals 3, right? So what's that point? 9, right? So now what we're going to do is we're going to have y equals 9, y equals 0. Okay? Now, instead of defining a rectangle that goes up and down, I'm going to define a rectangle that goes this way. So now what we're going to do is see if we can define a DA that looks like this. Now you really got to put your thinking cap on with this one. You got to pay attention. Okay? First off, what's the thickness? Before it was dx. Now what is it? dy. Okay. All right. Now, help me out. What is this dimension? 3. That dimension's 3. So now what we got to do is see if we can define this dimension and this dimension. So this is the curve, right? This is my curve that I'm looking at. So if I want to find the coordinates of some random point on the curve, the coordinates of this are x comma y, right? So if I propose that to go from here to here, from the origin out, is x. So if this is 3 and this is x, what's this? Say again? 3 minus x. You got to be careful with this. It's tempting to just say it's x. No, it's 3 minus x. Okay? Now, if you don't believe me, follow along with some calcs that I'm about to do. So first, would you agree with that? Is that okay? Would you agree then that 3 minus x, you agree with that? So far, so good? So how about this? Would you agree with that? I know I'm getting a little wild on you here. I've got this definition for dA. Is there a way of testing if I got that right? I got a way. How about this? How about this? Let's compute the area with it. Now, in order to compute the area, I need limits. What are my limits going to be? Say again? 0 to what? 0 to 9. Hence why I'm going to write y equals 0 to y equals 9. Let's see if this works. All right? Let's break out some of those calculus skills. So what's the integral going to be? All right, so we have 3, the integral of 3. Normally it's 3x, right? But I'm integrating in terms of y. So that's going to be 3y minus, let's see if y'all remember how to do this. How do you integrate y to the half? Y to the 3 halves divided by 3 halves, right? But dividing by 3 halves is the same as multiplying by 2/3, right? So can I say 2/3 y to the 3 halves? Is that fair? So let's chug that out. What do we get? We get 3 hold on. 3 times 9 minus 2/3, 9 to the 3/2. Here, let's be a little cognizant of my symbology. Minus, and then everything else is going to be 0, right? Because I plug in the top number minus plug in the bottom number, but I'm going to get 0 for everything on the bottom number. So what do I get over here? I get 3 times 9, which is 27, minus 2/3 times, okay, well, let's see. 9 raised to the 3/2. So I take the square root of 9, I get 3, right? 3 to the 3rd is 3 times 3 is 9 times 3 is 27, right? So 27. So that is 27 times 1 minus 2/3, which is 27 times 1/3. Therefore, area is 9. Same answer as I got before, right? So that's a test to see whether or not I have formulated it accurately, because I should get the same area as before. The area is 9. It doesn't care whether or not I integrate in terms of x or y. I better get the same area, right? So, but that's good, great, grand, wonderful, but why did I do this? Why did Dr. Mike make this weird, funky way of doing it? Because I need the other coordinate for the centroid, okay? And to do the other coordinate, what I need to do is evaluate qx, or the integral of y dA. So now I need this in terms of y. So I need integral from y equals 0 to y equals 9 of y times dA. But now what I'm going to do is I'm going to use my new formulation for dy. So what do I get? So let's see. I get 3y minus, okay, so y times y to the half. What's that? Is that y to the 3/2? Isn't that right? Now I can start doing some integration. So help me out. What's the integral of 3y going to be? 3 times what? What's the integral of y? Y squared over 2. So 3/2 y squared. Is everybody with me so far on the calculus? Am I going too fast on this? Tell me if I am. Okay. Minus, all right, now let's pay attention. So we have the integral of y to the 3/2. So y to the 3/2 plus 1, that's y to the 5/2, divided by 5/2, but dividing by 5/2 is the same as multiplying by 2/5. So far, so good? So then, let's see. So again, plug in the top number minus plug in the bottom number. We know if we plug in the bottom number, we're going to get 0. So really all we have to do is plug in the top number. So what do we got here? We got 3/2 times 81. We've got 2/5 times 9 raised to the 5/2. This is one of those things that you might as well surrender to the Casio FX115 ES Plus or similar scientific calculator. When it's all said and done, you end up getting, Well, actually, somebody verify me on this. I got that. Did anybody else get that? I see a few people raising their hands. So yeah, when you chug that out, you get 243 over 10. So therefore, bless you. If you want Y bar, it's just that, or that. And so this is 243 over 10 divided by 9. And so this ultimately ends up being 27 over 10. So therefore, hold on. Y bar is 2.7. So, if you want to print this out on a MakerBot and get a thumbtack and see if you can balance it, try and balance it on that point right there, and it should work. I'll go back down here. What do you think? Breaking out all the calculus, I know at 8 o'clock in the morning is a little rough. But I will tell you that that is probably the most difficult calculus we will do this entire semester. This is it. So, all right. Any questions? All right, I want to show you something real quick. I really want y'all, and part of me is showing you this so that it's on the recording. Okay? So, this is going to be your homework assignment on this. So what I've done is I've given you a region that's basically a right triangle, okay? And you're going to derive the coordinates of the centroid of this. Now, what I will tell you is that the problem, so a couple things. Number one, the integration itself should be easier because you're not integrating with a parabola, you're integrating with a line. So it actually should be easier. One thing that might be a little challenging is the fact that you're dealing with letters instead of numbers. Like the numbers we had in the last time were 3 and 9, and now you're going to have B and H. So I've given you a couple of hints. So the first hint is try and determine the equation of this line. Like y equals mx plus b. What is the equation of this line? What is the slope of that line? What is the intercept of that line? That should make it easier to determine not only the equation of that line, but the area of those blocks. Okay, so that's point one. Point two is during your integration, you're going to have some alphabet soup. Treat the letter B and the letter H as constants, because that's what they are. Okay, so treat them as you would the number 3 or the number 6 or whatever. Okay, you should get some very nice, neat fractional answers at the end. It should be very simple. Okay. And I'll go ahead and tell you is that at least the Y one should match what's in the textbook, okay? And I will say that the dependent upon how the triangle is oriented, one of the ones that's in the textbook might match, the other one might not. But if you pay attention to the diagrams in the textbook and to what you're integrating, you can probably glean, what's going on. I don't want to say any more than that because at some point you have to do a little bit of the work. Sound good? All right. Don't forget, we have exam review on Wednesday, so come prepared asking questions. I'm going to pull up the QR code again. That's all I've got. I will see you all on Wednesday.